Hello, this is Serene from Exam Help Lab. Today I'll be solving Physics Paper 2 AS Level Structured Questions 9702 Paper 2 Variant 1, 8 June 2020. Question number 1, Part A. Use an expression for work done in terms of force to show that the SI base units of energy are kilograms meters square per second squared. So work done is equals to force into distance in the force's direction, where force has SI base units of kilograms meters per second square and unit for distance is meters. Hence, for work done or energy transferred, SI base unit is kilograms meters square per second square. Part B1, the energy E stored in an electrical component is given by E is equals to Q squared divided by 2C, where Q is charge and C is a constant. Use this equation in the information in Part 1 to determine the SI base units of C. So after rearrangement of formula, C gets Q squared by 2E, where we will ignore 2 for finding the SI base units of C, where Q square is equals to ampere square and second square divided by the SI base units of energy from Part 1 is kg meter square per second square. So this becomes ampere square s to the power 4 per kilogram per meter square. Part 2, measurements of a constant current in a wire are taken using an analog ammeter. So that's not a digital one, but an analog ammeter where you have got a needle which deflects. For these measurements, describe one possible cause of a random error. So random errors are usually resulting from experimenters' way of taking some kind of measurement incorrectly. Like over here in analog meter, it has got a needle which deflects, but not a digital value. So a random error may occur over here if you take values from different angles. So you can write over here that reading of scale from different angles. Systematic error. Systematic errors occur due to some fault with the instrument or there is low precision of the device. So you can write over here that if ammeter is not calibrated correctly before you start taking measurements, so a zero error might cause a systematic error in your readings. Question number 2, Part A, state Newton's second law of motion. So Newton's second law of motion states a formula that is resultant force is equals to mass into acceleration. Acceleration is equals to rate of change in velocity, and that resultant force in terms of momentum is that resultant force is equal to rate of change of momentum. Part B, a delivery company suggests using a remote-controlled aircraft to drop a parcel into a garden of a customer. When the aircraft is vertically above point P on the ground, it releases the parcel with a velocity that is horizontal and of magnitude 5.4 meters per second. So the horizontal velocity with which the parcel is going to travel towards the ground is 5.4 meters per second. The path of the parcel is shown in figure 2.1. So this path over here is a projectile motion, means this parcel has got a vertical component being covered and a horizontal component being covered. So the parcel takes a time of 0.81 seconds after its release to reach point Q on the horizontal ground. Assume air resistance is negligible. So the time taken by the parcel to reach from this point to this Q point, both in horizontal components and vertical components, is 0.81 seconds. Part 1, on figure 2.1, draw an arrow from point X to show the direction of the acceleration of parcel when it is at that point. So, so since the parcel is in projectile motion, it must have a horizontal component of its motion and also its vertical component of motion. Its horizontal component has a constant velocity throughout its motion, meaning there is going to be no acceleration, there's going to be no resultant force in the horizontal motion towards the right, while in vertical motion there's going to be acceleration due to the gravitational effect, and that's g, and that's 9.81. So there's going to be acceleration vertically downwards due to g. And it is also said that air resistance is negligible, so this acceleration is on hold because of g. Part 2, determine the height h of the parcel above the ground when it is released. So we'll consider this particle's vertical component in this part of question. It will have initial speed 0 because it is traveling from height and then reaching point Q. So and time taken is going to be the same for both components, meaning 0.81 seconds for horizontal path of its motion and vertical path of its motion. So t is equals to 0.81 seconds. It takes this amount of time to reach from this point until Q. And acceleration is going to be all 9.81 since we are neglecting air resistance. And we are asked to find the distance it travels. So we can use this formula, S is equals to ut plus half AD square. So S is equals to half into 9.81 into 0.81 square. And you get h as 3.22 meters. Part 3, calculate the horizontal distance d between points P and Q. So horizontal distance is always going to be speed into time. The speed was initially told to us right over here, that the parcel is going to travel with a horizontal speed of 5.4 meters per second. So 5.4 into the time interval also was given to us in the beginning. So this is 0.81, and you get horizontal distance being covered by the parcel as 4.4 meters. Part C, another parcel is accidentally released from rest by a different aircraft when it is hovering at a great height above ground. Air resistance is now significant, so the acceleration on the parcel is not going to be alone due to g now, because air resistance is in action. Part 1, on figure 2.2, draw arrows to show the directions of the forces acting on the parcel as it falls vertically downwards. Label each arrow with the name of the force. So there's always going to be weight acting right from the center of the parcel, so we'll label it weight. And since air resistance is now significant, so there's going to be air resistance acting against the motion of the parcel. So these two are the forces currently acting on this parcel. Part 2, by considering the forces acting on the parcel, state and explain the variation, if any, of the acceleration of the parcel as it moves downwards before it reaches constant terminal speed. So in case of terminal velocity, you need to remember that the object first will move with increasing acceleration because there's only weight acting on the object initially. But the faster it starts to travel, the air resistance starts to increase acting on the object. Weight although remains constant, but with increase in air resistance, the resultant force decreases. And when that happens, of course, acceleration would decrease too, according to the formula. Resultant force is equals to mass into acceleration, where resultant force and acceleration, they are directly proportional to each other. So you can write over here that with increase in air resistance as it travels downwards, resultant force decreases, and hence acceleration decreases too. Part 3, describe the energy conversion that occurs when the parcel is falling through air at constant terminal speed. So at constant terminal speed, it isn't gaining any kind of kinetic energy. So all the GPE is getting converted to thermal energy, to air resistance. Question number 3, part A, state two conditions for an object to be in equilibrium. So there is going to be resultant moment about a point is 0 and 0 resultant force. Part B, a sphere of weight 2.4 newtons is suspended by a wire from a fixed point B. A horizontal string is used to hold the sphere in equilibrium with the wire at an angle of 53 degrees to the horizontal. So the sphere is in equilibrium. As shown in figure 3.1, part 1, calculate the tension T in the wire. So the sphere is currently at rest, it is at equilibrium. This means that all upward forces acting on the sphere are equal to all the downward forces acting on the same sphere. So the upward force acting on this sphere is only the vertical component of tension T, which is equal to T sine 53, and the downward force acting on the sphere is weight, which means that the weight is equals to the vertical component of tension T, and that's how you get T is equals to 3 newtons. The force F exerted by the string on the sphere, so again it is at rest, meaning all the forces acting towards the right will be equal to all the forces acting towards the left. So the force acting towards the right is the horizontal component of tension T. So this horizontal component is equals to T cos 53. So F is equals to T cos 53, and since it is 3, so 3 into cos 53 is going to be equal to 1.8 newtons. Part 2, the wire has a circular cross-section of diameter 0.5 millimeters. So you must convert that to meters. And it is diameter, so we'll divide it by 2 to get this in radius. Determine the stress in the wire. So stress is equals to force divided by area. So stress on the wire can be calculated by taking the force, which is the resultant of force in string and the weight. So weight has a magnitude of 2.4 newtons, and string has a magnitude of 1.8 newtons. So the resultant of 1.8 and 2.4 will get me the stress. So 1.8 and 2.4. And the area is that pi r square. That's 62.5 into 10 to the power negative 9 by 1.53 into 10 to the power of 7 pascals. Part C, the string is disconnected from the sphere in part B. The sphere then swings from its initial rest position A, as illustrated in figure 3.2. The sphere reaches maximum speed when it is at the bottom of the swing at position B. The distance between P and the center of the sphere is 75 centimeters. Air resistance is negligible, and energy losses at P are negligible too. Part 1 showed that the vertical distance h between A and B is 15 centimeters. So this distance between the center of the sphere and point B is 75 centimeters. So this distance must be 75 sine 53, which is equal to 59.9 centimeters. And this in total should be 75 too, because when ball comes to position B, it is again the distance. This whole distance is again the distance between the center of sphere and point B. So this whole will be 75, and this only this is 59.9, means the difference is of 75 minus 59.9, and that gives me a vertical distance h as 15.1 centimeters, which is also equal to 15 centimeters. Part 2, calculate the change in gravitational potential energy of the sphere as it moves from point A to B. So the change in height is of 15.1 centimeters. So the loss in gravitational potential energy is equal to m into g into h, where m into g for the sphere, which is the weight of the sphere, is 2.4 into the difference in the height is 15.1 divided by 100, so that changes to meters, and the change in gravitational potential energy is of 0.36 joules. Part 3, use your answer in C. Part 2, to determine the speed of the sphere at B. So because the sphere is decreasing its height, there is going to be loss in GPE is equal to gain in kinetic energy. Loss in GP is of 0.36, and kinetic energy at its initial position is 0. So 1 by 2 into the mass of the ball. The weight of the ball is 2.4 divided by 9.81 to get the mass into speed square. So speed is equal to 1.716 meters per second. Question number 4, part A1. By reference to the direction of propagation of energy, state what is meant by longitudinal wave. So a longitudinal wave has vibrations of particles parallel to direction of energy propagation. Part 2, state the principle of superposition. So superposition takes place when incoming waves overlap and resultant displacement is equal to sum of individual displacements. Means the displacement for the resultant wave will be the sum of individual displacements of waves. Part B, the wavelength of light from a laser is determined using the apparatus shown in figure 4.1. The light from the laser is incident normally on the plane of the double slit. The separation of the two slits is 3.7 into 10 to the power of negative 4 meters. The screen is parallel to the plane of the double slit. The distance between the screen and the double slit is 2.3 meters. A pattern of bright fringes and dark fringes is seen on the screen. The separation of adjacent bright fringes on the screen is 4.3 into 10 to the power negative 3 meters. Part 1, calculate the wavelength in nanometers of the light. So the formula for the young double slit experiment is AX by D is equals to lambda, where A is distance between the two slits, X is the distance between two adjacent bright or dark fringes, while D is distance between the two slits and screen. So distance between two slits is 3.7 into 10 to the power of negative 4 meters into distance between adjacent bright fringes is 4.3 into 10 to the power of negative 3 meters divided by distance between the two slits and the screen is 2.3 meters. This will give us the wavelength in meters, so we need to multiply that to 10 to the power 9 to convert that to nanometers, and you get a wavelength as 690 nanometers. Part 2, the intensity of the light passing through each slit was initially the same. The intensity of the light through one of the slits is now reduced. Compare the appearance of the fringes before and after the change of intensity. So intensity has a relationship with only amplitude, so there is going to be no change in any kind of appearance of the fringes, like there is going to be no change in fringe separation. The only thing which will change is going to be the darkness or the brightness So because the intensity was reduced, so the bright fringes will get darker and dark fringes get brighter. It will be vice versa if the intensity of the light was increased. Question number 5, part A. Metal wire is used to connect a power supply to a lamp. The wire has a total resistance of 3.4 ohms and metal has a resistivity of 2.6 into 10 to the power of -8 ohm meter. The total length of the wire is 59 meters. Show that the wire has a cross-sectional area of 4.5 into 10 to the power of -7 meters squared. So resistance has a formula of resistivity into length divided by area, where resistance is 3.4 ohms, resistivity is 2.6 into 10 to the power of -8. The total length of the wire is 59 and area is unknown. So you get area as 4.5 into 10 to the power of -7 meters squared. This has been proven. Part 2, the potential difference across the total length of wire is 1.8 volts. Calculate the current. So current is equals to voltage divided by resistance, where voltage across the wire is 1.8 and resistance of wire is 3.4 ohms, and you get a current of 0.53 amperes. Part 3, the number density of the free electrons in the wire is 6.1 into 10 to the power of 28 per meter cube. Calculate the average drift speed of the free electrons in the wire. So current is equals to number density into cross-sectional area into average speed into the charge of an electron. The current through that wire is 0.53. Number density is 6.1 into 10 to the power of 28. And the cross-sectional area is what we calculated in part 1. So that is 4.5 into 10 to the power of -7. Into drift speed into a charge for a single electron is 1.6 into 10 to the power of -19, and you get an average speed of 1.21 into 10 to the power of -4 meters per second. Part B, a different wire carries a current. This wire has a part that is thinner than the rest of the wire as shown in figure 5.1. Part 1, state and explain qualitatively how the average drift speed of the free electrons in the thinner part compares with that in the rest of the wire. So a thinner part means that area decreases, and according to the formula, I is equals to N into A into V, area is inversely proportional to drift speed. So we can write that area is reduced and hence drift speed increases because they're inversely proportional to each other. Part 2, state and explain whether the power dissipated in the thinner part is the same, less or more than the power dissipated in an equal length of the rest of the wire. So power dissipation has a formula I square R, and according to the formula I is equals to NAVE. Area is inversely proportional to resistance. A thinner part means that area decreases and resistance would increase, and when resistance increases, power dissipated would increase too. So we can write again that area is reduced and resistance increases. Thus, power dissipated is more. Part C, 3 resistors have resistance of 118 ohms, 90 ohms, and 30 ohms. Sketch a diagram showing how 2 of these 3 resistors may be connected together to give a combined resistance of 60 ohms. Okay, so combined resistance of 180 ohms and 90 ohms will give us combined resistance of 60, because 180 into 90 over 180 plus 90, that gives me 60 ohms. Part 2. A potential divider circuit is produced by connecting the three resistors to a battery of electromotive force 12 volts and negligible internal resistance. The potential divider circuit provides an output potential difference of 8 volts. On figure 5.2, label the resistances of all three resistors and the potential difference V out. So the resistors we have got here is 180 ohms, 90 ohms, and 30 ohms. We still have no idea whether 8 volts of V out is across this resistor or across this parallel connection of two resistors. Okay, and now if we put 180 ohms here in series with parallel combination of 90 ohms and 30 ohms, let's say we calculate V out across 180 ohms. So V out across 180 ohms of resistor is going to be 180 into 12 divided by 180 plus combined resistance of 90 and 30, which is 22.5. That gives me a voltage of 10.7 volts across 180 ohms. This means that voltage across parallel combination of 90 and 30 would be 1.33 volts. That is subtraction of 10.7 and 12. Neither of these is giving me V out of 8 volts, means this is not possible. Now, what if we put 90 ohms here and 180 in parallel with 30 ohms? If we calculate V out across 90 ohms, it is going to be 90 into 12 divided by 90 plus combined resistance of 180 and 30 is 25.7, and that gives me a voltage of 9.33 volts. This means that 9.33 volts is the voltage across 90 ohms, and rest of it, which is 2.67 volts, is across this parallel combination of 180 and 30. Again, neither of these voltages is 8 volts, means this case is not possible too. Now, what if we put 30 ohms here in series with parallel connection of 180 ohms and 90 ohms? If we calculate voltage across 90 ohms, it will be 30 into 12 divided by 30 plus the combined resistance of 180 and 90, which is 60 ohms. That gives me a voltage of 4 volts. 4 volts of voltage is across this 30 ohms, which is in series with parallel connection. This means that a voltage across 180 ohms and 90 ohms of parallel loop is going to be 12 minus 4, which is 8 volts. So here I get the V out of 8 volts, and I'll label this as V out. And 30 ohms is in series with the parallel connection of 180 and 90 ohms. Question number 6, part A. Two horizontal metal plates are separated by a distance of 2 centimeters, which is also 0.02 meters. In a vacuum as shown in figure 6.1, the top plate has an electrical potential of positive 180 volts and the bottom plate has an electric potential of negative 120 volts. Part 1. Determine the magnitude of the electric field strength between the plates. So electric field strength is equals to voltage divided by the distance. The voltage we have over here is positive 180 minus 120 divided by the distance is of 0.02 meters, and we get an electric field strength of 15,000 magnitude. Part 2. State the direction of the electric field. So electric field is from the more positive plate to more negative plate, so it's going to be from positive 180 to negative 120. So this is going to be vertically downwards. Part B. An uncharged atom of uranium-238 has a change made to its number of orbital electrons. So the change is only in orbital electrons. This causes the atom to change into a new particle that has an overall charge of plus 2e, where e is the elementary charge. Part 1. Determine the number of protons, neutrons, and electrons in the particle X. So uranium-238 changes to some X ion, which has a total charge of plus 2. This means that the orientation on the left remains the same because this thing 238 is the number of neutrons and protons, and this is the number of protons, and there is only going to be change with number of electrons. So the number of protons remain 92, number of neutrons remain 238 minus 92, which is 146, and number of electrons will decrease by 2, that becomes 90. Part 2. The particle acts as an electric field in Part A at a point midway between the plates. Determine the magnitude of electric force. So electric force is equals to electric field strength into the particle's charge. Electric field strength from the previous part is 15,000 into the charge of ion X is positive 2e. So into 2, and E has a magnitude of 1.6 into 10 to the power of negative 19, and you get a force of 4.8 into 10 to the power of negative 15 newtons. The nucleus of uranium decays in stages by emitting alpha particles and beta minus particles to form a nucleus of thorium-230. Calculate the total number of alpha particles and the total number of beta minus particles. So uranium-238 92 converts to alpha particles, beta minus particles, and thorium. Now we need to balance the nuclear number and the number of protons both on the left and the right side. So here it is 230 plus 4, that makes up to 234, and over here there are 238, a nucleon number. So we can add 2 alpha particles to make it 2 into 4, 8, and then 230. 230 plus 8 is going to make up to 238. So we will have 2 alpha particles. Now we need to also balance the number of protons, or you can say charges, on both sides of equation. Over here I've got 92, while on the right side we have 90 plus 4, which is 94, and then minus 1, 93. So what if we add 2 beta particles to make 90 minus 2, which is 88, plus 4, which becomes 92. So now on both sides of equation they have been balanced. So there are going to be 2 beta minus particles. That's the end of the paper. Thank you for watching.